Hello, everyone. Thank you so much for having me. Really excited to be here. And yeah, this isn't my first async, so really nice to be back. Thank you for having me back. So my name is Sophie. I'm an engineer at Incident.io, as you said, Steve, and we build software that helps companies like create and manage and resolve incidents in Slack. So it's kind of like creating incident channels, coordinating everything, hooking up with external things like Jira, Linear, GitHub to make sure that you can then export all your things. And I think it's great. Not as like, it doesn't have the kind of exciting, oh, you work for Monzo, that's super cool. But I'm hoping that soon people will be like, oh, you work for Incident, that's super cool. Happy to chat that kind of thing afterwards. I'm also a keen musician. So I arranged and conduct pop songs at my choir. We've just come back after like a 2-year hiatus, which is amazing. And I make music myself as well. I have a website where I blog about tech stuff, and you can find me on Twitter if you prefer shit posts. Do find me. So this is what I'm going to talk to you about today. This is my virtual piano. You can click the keys and it will play notes. If you choose different scales, it plays scales and chords. And I'm going to talk to you about the musical theory behind it and tell you how it works. And I'll show you a bit of the API that powers it, which is the Web Audio API. So some background on how this came about. My choir has a retreat every year. It's like a weekend filled with singing and workshops and wine and crying. And this year, for obvious reasons, for the last couple of years, we haven't been able to get together in person. So we decided last year to have a virtual retreat. And I decided it was a great opportunity to give a workshop on musical theory. It's something that I've kind of absorbed over the years, playing various instruments, but people in the choir didn't really have a musical background. So usually with a workshop like this, I'd give the attendees some resources, some exercises to put into practice what they've learned. So if we were learning about different chords, for example, I might split the attendees into groups and get them each to sing a different note of a chord to see how it sounds together. And you can't do that over Zoom. It doesn't work. We tried. So I kind of thought, are there any other ways I could maybe get people to try out chords and scales to see how they sound? Well, what if I had a web app that did that? And yeah, I realized there's almost certainly already a web app that did that. But I saw a really big opportunity to not do the work I was supposed to be doing and instead build something really stupid in JavaScript. Because procrastination is definitely one of the greatest passions in my life. So it seems appropriate to start with a bit of musical theory and the science behind it, because the theory that I was teaching in the workshop actually did go into the app itself, which I think is quite cool. And I know not all of you might be familiar with the technology, so I'll kind of cover some relevant terms as well. So sound is made up of vibrations which travel as waves. And the number of vibrations in a set time period is what we call the frequency of the sound. And we measure frequency in hertz, which is one cycle of the wave per second. And with the keys on a real piano, you've got hammers hitting the strings inside the piano, and those strings vibrate at a particular frequency to make different notes. And Western music uses a set of tones with specific frequencies. So in music, we refer to those individual sounds as notes, particularly in written music. So the system that we use in the UK and US has 12 notes. Each has a letter, A to G, although that's only 7 letters. And in between those 7 letters, there are 5 accidentals. And these are notes which sound very similar to the ones either side. And they don't get their own letter because of that. And instead, we give them a symbol and we call them sharp or flat, depending on which way we're looking. And an accidental is sharp compared to the note below it and flat compared to the note above it. So each accidental actually has 2 names, which you would be able to see if the formatting hadn't got a bit messed up on this slide. So C sharp is also D flat. And the division of the notes is actually based on the frequency of each note. And if you want to know more, I recommend looking at the Wikipedia page on musical notes. There's a great Wikipedia hole to fall down there. But as I mentioned, not all countries have the same letters. So in Germany, what I call a B flat is called a B, and what I call a B is what they call an H. And the composer Bach played a little note pattern in a lot of his songs that went B flat, A, C, B, or in Germany, it spells out B, A, C, H, giving himself a little shout out in his own songs. The distance between any note and its nearest neighbor, so C to C sharp or D to D sharp, E to F, is called a semitone or a half tone in the States, and 2 semitones makes a tone. So generally, when we're talking about musical notes, we're referring to them as they're laid out on the piano, starting from C. And the letters of the notes repeat for all of the notes on the piano in groups, from the lowest on the left to the highest on the right. And a piano has white and black notes. The black notes are accidentals. And again, if the black note's to the right, it's a sharp. If it's to the left, it's a flat. And the distance between one note and its next occurrence, so A to A on the piano, is an octave. And on a regular piano with 88 keys, there are 7 1/4 octaves. And those octaves are pitched higher and lower relative to each other. So I've got 2 notes here. One's in A and one, well, they're both A. One's in octave 4 and one's in octave 5. And it's a weird quirk of our brains that we can actually hear 2 notes of the same letter in different octaves and just kind of tell that they're the same note, but one is higher and one is lower. And each octave jump actually doubles the frequency of the note. So that first A that I played you, it's A4 because it's in the 4th octave, and that's 440 hertz. And A5 in the octave above is 880 hertz. And music tends to use only some notes, so not all of them. And each note on a piano has a set of 8 notes that you can play after it to reach the next octave. And that's what we call a scale. And in English, the word scale used to mean ladder. And so it's kind of a bit like a ladder to the next octave. So when we use those notes from a particular scale throughout a piece or a song, that's what we mean by key. So when you talk about what key a piece is in, that's which scale do we take the notes from, basically. So this picture shows 2 octaves of the C major scale written in musical notation. And the important thing to note about scales for this talk is that they follow particular patterns. And you can apply a particular pattern to any note and you can get the associated scale starting from that note. And as programmers, we love patterns. So in this example, which is the G major scale, you can see the pattern that creates the major scale. So if we remember that 1 semitone is the distance between one note and its right-hand neighbor, and a tone is 2 semitones, then we get tone, tone, semitone, tone, 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 semitone. And if we apply that pattern to any note on the piano, we'll get that major scale. Cool, code now, please. This is not a music meetup, this is JS meetup. So let's talk about the Web Audio API. It's a really powerful API. You can do some really cool stuff with it. So you can play audio files, you can synthesize audio, which is what I'm doing in this talk. You can analyze audio that's playing, do some kind of Winamp visualization stuff, manipulate playing audio, so mixing, filtering, panning, all sorts of things. It's really cool. And we talked about sound waves before and the frequencies of the waves that shape the waveform. And synthesizers actually generate these waves programmatically to make sound. And that's what we need to do in order to make JavaScript music, basically. So we're going to build a little synthesizer, and we need an oscillator, which in real life is a circuit that produces an alternating waveform. And then we need to tell it what that waveform should be. And we need to know the frequencies of all the notes on the piano to tell the synthesizer what note to play when we press a virtual piano key. And then we need to actually build those piano keys. So we need a UI as well. So to get started, we need to get access to the API. And we do that by initializing an audio context. And this is an interface that exists on the window object in the big 4 browsers. And we only want one of these in the app, because if we had multiple audio contexts, we could have lots of sounds playing at once, which we don't want. And this instance of the audio context will give us lots of functions and let us interact with the API. And now we need to create the waveform that our synthesizer is going to output, basically. So the shape of this waveform will determine the sound that's played. So a sine wave which is the curvy one, will make a very different sound to a square wave, for example. It's a sine wave, and that's a square wave. And the audio context object that we instantiated in the last slide will give us a function that's called create periodic wave, which takes two arguments. They are arrays of floats, and they define the various values of the wave. And for the purposes of this project, I just wanted something that vaguely resembled a piano. And vaguely is the term here because generally software pianos use samples of real pianos. So they're actually like recorded. And that really wasn't an option for this tiny project. So I just kind of Googled for web audio waveforms. I found a bank of pre-made sounds, and I just thought, you know what, that'll do. They're kind of okay sounding, sounds nothing like a piano, but that wasn't really the point. So now we've got our waveform, we need to create the oscillator that's going to turn that waveform into sound. And an oscillator generates a constant tone. So we create the oscillator with the function create oscillator, and then we set the wave that we've just created, and we'll connect the oscillator to the audio context destination. So this is by default, basically the speakers effectively, but you could pipe it to probably another, well, you could pipe it anywhere really. So maybe another audio context or something. And then we start the oscillator to get it going. And at this point, the app will actually be playing a fixed tone. So it defaults to A4, 440 hertz. So how do we tell it to play a different note? Well, in order to go from the note, letter, and octave to a frequency, I needed to do some maths. So we use that note A4 as a constant. It's A above middle C on the piano, and it's actually standardized as ISO 16 as a reference pitch to tune instruments by. And as I said, its frequency is 440 hertz, which is a nice round number. A lot of the other notes have decimals as their frequencies. So that equation, we've got the frequency is 440 hertz multiplied by 2 to the power of n over 12. And n in the equation here is the number of semitones we need to go from A4 to the note. For example, the note C5 is the next C above A4 on the piano. That's a difference of 3 semitones. I'll explain it, don't worry. So the intervals that we use to calculate the steps between the notes are actually hard-coded based on a single octave. So if I was looking for a note in the same octave as A4, like what would the interval be? So this is all the semitone distance of all the notes in a single octave from A. And this is how I translated that equation to code. So this function takes a note, letter, and a number combination, such as C5, which is C in the 5th octave of the piano, and it gives us the frequency. So first, we need to find the interval corresponding to that note within the octave from the hard-coded list. And then we calculate the number of steps from A4 to our note by first working out the difference in octaves between the octave that we're looking for and the 4th octave where A4 lives. And then we multiply it by the number of semitones in an octave, which is 12. And then we add the original interval. And finally, we can calculate that frequency by running the equation that we saw before, which is the value of A4 multiplied by 2 to the power of the number of steps over 12. And then for convenience, I round it to 1 decimal place. So in this example, for the note C5, we subtract our base octave 4 from the octave 5, and that gives us 1. 1 times 12 is 12. And then we add -9, which is the interval from A to C that we got from that object. And this gives us 3, and that's the number of steps between A4 and C5. And then we feed that into the formula, we get a frequency of 523.3. And with these frequencies, I can now generate octaves of notes in the form of arrays. So I use these to supply notes to the virtual piano, and I can generate things like chords and scales. So I iterated over the notes in order, and I calculated the frequency of each one and appended them to an array. So now that we've got the frequencies, we can build the piano. I built it in React. Vanilla JavaScript would have worked just as well. I ported over a JavaScript library called Piano SVG into React because I didn't want to build my own from scratch. And each note is assigned a numeric ID based on its position in the array of frequencies I generated. So each key is an SVG path that's rendered by a separate React component with its own props. and it includes the ID of the note that it represents. And this way I can pass in whether or not it's being played and what happens when you click it as well. So I added an on mouse down handler to each key, which sets the oscillator frequency to the frequency at that position in the array. And then I added an on mouse up handler to stop it when you release the mouse button. And the piano SVG code takes care of like calculating the positions of the keys. My piano component renders 2 rows, which is 1 white and 1 black. I won't go into the details of rendering it itself. It's on GitHub as well. So with the piano rendered, I could pass in functions to trigger on the key, on click, basically. So as I mentioned, it takes an array of notes. The key component has its own ID. The piano itself sits inside a player component, which controls all of the audio operations and manages what's currently playing. And I wanted to be able to press a note and have it sound once, but I also wanted to kind of activate like a sustain pedal so that you could release the mouse button, but still have notes playing. And I also wanted it to be keyboard accessible as well. So the player component stores whether or not the pedal is active in state, and each key has a ridiculous number of event listeners. So there's on-click listeners that play and stop notes when the pedal's active, and then the mouse up and mouse down listeners play and stop when the pedal is off. So as soon as you release the mouse, it'll stop. And I define those play and stop functions in the parent player component and pass that into the piano. And then we actually create a new oscillator for each note that plays, because an oscillator can only play one note at a time. So to play multiple notes at once, you need multiple oscillators. And I keep track of all of those oscillators in the player state, and I stop and disconnect them when we're done with them, basically. There is a lot of code that goes into this. So if you're interested in the particulars, I do recommend looking at the GitHub repo as well. So as well as being able to interact with the piano directly, I wanted to be able to automatically play all the notes in a particular scale. So if you remember how the scales have like predictable patterns, we can use those to generate the notes of a scale. And I put together this table of intervals for various scales where each number is the interval of the next note from the previous note. And the first number is always the starting note, always 0, unless we're starting from the top and going down again. So with the major scale, which is the first one in this list, the pattern is tone, tone, semitone, tone, 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 semitone. And if you think of all these numbers as semitones, a tone is 2 semitones. So 0, 2, 2, 1, 2, 2, 2, 1. And then I generated an octave of notes, and I iterated through the scale pattern, fetching each note based on a cursor that I kind of kept track of the current position, which note that we're currently on. And then we add each interval to the current note to find the next note in the octave array. And when it comes to playing the scale, we need to change the frequency the oscillator is playing at regular intervals as we go through the scale. So we set timeouts for each note in the scale. In this case, it's ½ a second. And we multiply the timeout by the index of the note so that in the array so that they're staggered. And when the timeout elapses, the frequency changes to whichever note it is in the array. And we end up with this really nice sequence of timeouts. And the player keeps track of these timeouts in the state so that if the user hit the stop button, I can then cancel all of the timeouts and stop the scale playing. So I got it all working, but I had a bit of a nightmare with it. For one thing, sometimes the notes just don't stop. Despite like keeping track of all the oscillators and all of that, it just seems to lose track sometimes. It just can't disconnect them. And sometimes like initializing oscillators didn't work fast enough. So I'd get errors from trying to set frequency on undefined things. And I had to wrap the initialization function in a promise to force the app to wait until the oscillator had actually been initialized. But I decided that people can just refresh the page and live with it. And also, yeah, it's a bit gross from an accessibility point of view. Like you can't have a button inside an SVG. So like there's a lot of SVGs with on-click attributes, which is usually a bit of a no from accessibility point of view. But I ran with it, added an ARIA attribute, role equals button to each key. And then the display order of the keys didn't match the tabbing order because the white and black keys are rendered separately. So it went all the way through the white keys, then all the way through the black keys. So I had to like manually override the tab index, which is also another kind of yikes thing. But effectively got there in the end, and it is keyboard usable now. So I'm going to attempt to show you this. Protect your ears. There's a C major scale. You can play a chord. Accurate. We can put the pedal on. There we go. Last time, see, just gets stuck. It's ridiculous. There we go. So like last time I did this at a meetup, someone actually like in the chat wrote like my ears. So I apologize if anyone was personally offended by that. There are some other features I didn't show you in this talk. It kind of, it plays various different chords. It shows you what note it's playing as well. And if you'd like to see it for yourself, it's all on GitHub. The app is hosted on Vercel. So it's virtualpiano.vercel.app. Thank you very much for listening.